Welcome, everybody. Welcome back to the SML Journal Club. Today we are doing only by remote because we have Paolo Morettin that is now in Leuven.
Hello.
He was a PhD student here at the University of Trento under the supervision of Andrea Passerini and Roberto Sebastiani. He was a visiting student at UCD in Dublin, at the Catholic University of Leuven and UCLA in Los Angeles. So his main interests involve SMT and SAT, but also something else that we are curious to hear about. And so today is going to talk about learning and reasoning in with probabilistic SMT. So Paolo, you can start. Thank you for joining.
Thank you for inviting me. Thank you, everybody. Yep, as Emanuele said, my interests lie in intersection of probabilistic models and logics, or more in general constraints. And today I'm going to talk about my current research interests, a bit about what I've been doing during my PhD studies. It's going to be a long presentation, so I hope I don't lose you in the process. Yeah, I'm going to start my presentation with the usual slide on the concerns of modern artificial intelligence, raising questions like, is my AI going to kill me on purpose, by accident, or even better, can we avoid this? Can we try to enforce, guarantee, or verify some properties like robustness, safety in our AI system? And then my next slide is going to be something along the lines of, why do news outlets and blog posts do not talk about the risk of catching a flight or getting a computerized tomography scan, right? And the reason is mainly due to formal verification. Formal verification is a subfield of computer science that is devoted, as the name suggests, to formally verifying and guaranteeing that certain properties in our hardware and software systems are verified, right? So the traditional approach here is simple, let's say. You have a system S and a property of interest, and you basically use a formal or a logical language to encode these two concepts, and then you reduce the problem to one or a sequence really of decision problems. For instance, you use a SAT solver if you're using propositional logic, and you ask to this SAT solver whether there exists a possible world where this property of interest is not satisfied by the system. If your SAT solver returns yes, and then this truth assignment, this possible world, that means that we are in trouble. We have to go back and debug the system, right? This approach has been extended to other theories than purely logical theories. So theories like bit vectors, equality over uninterpreted functions, and of course also algebra, right? So this basically enabled the verification of even larger classes of systems, even continuous ones, and enabled us to verify properties like, if the elevator speed is greater than a certain threshold, the alarm should be on. All good until now. Then when this kind of approaches do fall short, well, for instance, if we need to quantify properties like robustness or fairness, of course, like a yes/no answer is not enough, right? Or if the system is not deterministic, then a purely logical approach is not enough. And most importantly, for this talk at least, when the environment that is the input of our system is high dimensional and uncertain, then of course this is a problem. Nonetheless, we would like to apply this kind, or at least have this kind of guarantees, apply this kind of techniques to applications like autonomous driving, right? Of course, if my autonomous car detects a speed limit of 120 miles per hour, and also a school crossing that doesn't make any sense. This is basically impossible in the real world, right? As a motivation, consider this input. This is a perfectly valid input for an autonomous vehicle, right? But what about this input? Maybe there's some kind of bug, I don't know, somewhere between the camera and my machine learning model, right? So then what about this one, right? This is, of course, very, very unlikely input for my model. The bottom line here is that there are some inputs that have such a low probability that we don't really care about those, right? That means that we need somehow to have a probabilistic model of the environment of the input of my system, and then we want to verify whether some properties hold or not with a certain probability. And this is called probabilistic formal verification. Now I'm gonna take one step back and assume, or better, to pretend that we can conveniently work with purely discrete models. We don't care about continuous variables anymore. Continuous variables are bad. Everything can be modeled with purely discrete distributions. And now I'm going to try to convince you that weighted model counting is really beneficial in developing safe AI systems. For those of you that are not familiar with the concept, weighted model counting is a logical task. As my name suggests, is the weighted sum of the models of a logical formula. Models here in logical jargon is really like a solution of a logical formula, or a truth assignments to the proposition that satisfy the formula. So if you have weight 1, for instance, weighted model counting becomes model counting, which is just summing, counting the number of solutions of a logical formula. By having a weight function, you basically give a different importance to the solutions of this formula. And you can interpret this weight as an unnormalized probability mass. So you have all the possible words which are defined by your formula, and you have a weight, non-negative weight, right? Typically, the weight is factorized as weights assigned to the literals. This is not important for the purposes of this presentation. What is really important is that you can reduce marginal inference in constrained discrete settings to weighted model counting. All you need to do basically is to compute the weighted model count of your query, let's say, in your probabilistic models, conjoined with the evidence, in this case A, and then you need to compute, of course, the partition function or the normalizing factor of your model in order to get like the probability between 0 and 1. So I said this is very beneficial in the development of safe AI applications. For instance, consider, well, you can use basically any probabilistic model, but here I'm going to use a probabilistic logic program P, possibly parametric. So here on the left, you see a problog program, for instance. It's a declarative approach where you basically have a number of clauses. Some clauses here have a certain weight. And this is a relational language, right? So how does inference and learning work in this setting? Well, first we need to ground this program. For those of you that are not familiar with the term, grounding means basically substituting every variable in our relation with an entity, let's say, and then we turn the program into a purely propositional program, and then we turn it into a logical formula plus some weights, as we have seen previously. Typically, what's done next is that we use knowledge compilation, which is a family of techniques that turns your logical specification into a compact structure that support the efficient computation of certain operations. For instance, in our case, what we care about is computing the weighted model counting efficiently. Another nice property of this kind of representation is that they're fully differentiable. So we can also use the very same compile structure to learn the parameters of our programs. But what is really important here ultimately is that in this way we have models that satisfy constraints by construction. They're guaranteed to satisfy our safety constraints, for instance. And for those of you that have worked with Problog or deep Problog, I'm looking at Gianluca here. Probably you know that weighted model counting based inference can be very slow, very expensive, even if you are like approximating some parts of the problem with neural networks. And in some applications, of course, we cannot afford this at inference time. We need something faster when we need to make some predictions, right? Can we still leverage our constraints? Of course, the answer is yes. Otherwise, I wouldn't have made this slide. Assume that we have a differentiable function, say a neural network that parameterize discrete distribution. Then we can use the so-called semantic loss to basically regularize our network during the training using gradient-based methods, for instance. So the weighted model, the semantic loss that you see here is nothing else than the logarithm minus the logarithm of the weighted model count of the constraint that we have, that we want to use to regularize the network, using as weights basically the output parameter of our model. And ultimately, it's just a big log polynomial. We want to evaluate this efficiently because we need to compute the gradients during the training. And the good news here is that we can still use knowledge compilation technique to find like a compact representation of our constraints. And in contrast with what I showed you earlier, the cool thing here is that at the end of the training, we can simply discard the circuit. And what we end up having is a model that satisfies constraints with high probability in expectation. Then you may ask me, yeah, but what does in expectation mean, right? Okay, I can use a test set, for instance, and then I can compute the ratio of predictions that satisfy the constraint. Our model is gonna satisfy the constraint 90% of the time. Of course, like this kind of point-wise evaluations are kind of misleading, depend on the test set. So then how can we be sure that the constraint is actually satisfied enough in the real world? Here comes formal verification or probabilistic formal verification. It has been shown recently, it's a 2019 paper, that if you have, say, a binarized neural network, these kind of models are really popular in embedded systems due to their very small memory footprint and fast inference. You can turn these binarized neural networks into a propositional logic formula. Of course, if you use like the trivial encoding, you're gonna get like a huge formula, huge encoding. So what people have been doing in BNN verification is that they use mixed integer linear programming. So they use a optimization procedure to find like an encoding that is equicardinal. What does an equicardinal encoding guarantee? Well, it has the same model count as the trivial encoding. And if you also want to specify like a prior on the input of your model, you can use a well-known reduction of weighted model counting to model counting. I'm not going to go, of course, into the detail because that will take hours. But ultimately, then you can use like an approximate model counter or weighted model counter for verifying quantitative properties like fairness and robustness to adversarial attacks, for instance. So I hope I convinced you that indeed we can use weighted model counting for many things. There are three kind of orthogonal directions here. Either we can use it for learning models that satisfy the constraints by construction. If we cannot afford that, then we can learn models that satisfy constraints in expectation by using the weighted model count as a kind of a regularizer, or we can use weighted model counting for verifying quantitative properties, basically by computing the probability that certain constraints are satisfied by the model. Now, what about continuous hybrid model? I initially assumed that we don't care about those, but this is clearly bullshit. And now I'm going to try to generalize what I've been telling you to this kind of hybrid or simply continuous models. In order to generalize weighted model counting, we first have to start generalizing the kind of representation language in weighted model counting is propositional logic. Here I'm going to use satisfiability modulo theories with algebraic constraints, like the one you see here. And I'm going to focus on linear algebra for this presentation. It doesn't have to be linear algebra, it can be also nonlinear, but it's easier for the purposes of this presentation. So here you can see a formula that encodes a non-convex region with two continuous variable and one propositional variable A. And then, of course, I need also to define kind of a density function on top of this, right? And well, on top of the continuous variables, of course. And here I'm going to use like this piecewise polynomial. You can see here that when propositional variable A is true, this density is a quadratic polynomial, and when is false is this non-quadratic linear polynomial in red here. And yeah, so let me define weighted model integration. So weighted model integration is a generalization of weighted model counting. Again, we are summing over all the possible words. W here is the unnormalized probability mass of each possible word. Now, this time, we also need to integrate the continuous variables out, right? We need to integrate these densities in order to get the actual probability mass. That sounds a bit scary. So let me give you like an example using the previous example here. What the weighted model integral of this problem would be. Well, I have a truth assignment, which then actually represents like a convex region, because it's like the conjunction of inequalities or equivalently the intersection of half spaces, right? So it's always going to be something convex, like the region here in blue. For this possible word, we have the quadratic term, because in this possible word, A is true. And I compute the integral of this density function, and I get the weight of this word. And I repeat this for every possible word, really. So this for assignment when A is true, and then finally to assignment when A is false, and that gives you like a different density, right? And that's it. This is the weighted model integral. Again, as in weighted model counting, this is going to give you unnormalized probabilities, unnormalized marginals. So then again, you need to compute the partition function in order to get like a small number between 0 and 1. Nonetheless, you can use this pretty much in the same way, and then you can support continuous as well as discrete variables and logical and also algebraic constraints. So this sounds cool, right? You can see that this weighted model integration task basically subsumes two tasks. The first one indeed is enumerating all these convex regions in the support of a distribution, or equivalently the constraints. And this is, of course, as hard as model counting, which is a Sharpie complete problem to solve exactly. And then the second task, of course, is integrating out the density function in this convex region. And this is also a very hard problem, because computing the volume of a convex polytope is Sharpie hard. So two very complex problems. The combination of the two is even trickier, because some of the successful ideas in weighted model counting do not apply here. And intuitively, the reason is because computing the unnormalized probability mass is not efficient, is not something that you can do efficiently anymore, because indeed you need to integrate some density function. So you may ask now, why do I even bother? Why spend my whole PhD doing this? Well, this is a very general framework, and many inference algorithms that you're using are indeed like specific subcases polytime weighted model integration in disguise, and trying to figure out what works best in the general case can definitely give some insights into also some subclasses of a problem. What does computing weighted model integration efficiently means? Well, consider the problem that I showed you earlier. I computed six integrals, right? Really, here I could have just computed two integrals. This one, so this convex region here using the quadratic term, plus this region here using the linear term, right? So two problems, two integrals instead of six. It's definitely nice. How this is done? How do these solvers try to compute this weighted model integral efficiently? Well, there's a bunch of techniques or combination of techniques. Again, knowledge compilation is typically used. Some works like what I've been working on during my PhD leverage some SMT solvers as oracles. Then there's some work also on exploiting properties of certain tractable subclasses of a problem. And of course, then you can always try to use Monte Carlo estimates as an approximation here. This is a table from last year survey that I wrote with Andrea Passerini and some people here at KU Leuven. In blue, you see the works I've been involved with, and in light blue, you see other solvers that people here at KU Leuven worked on. And it's a fairly recent formalism, and research until this point has focused mostly on theory and algorithms, of course, that was needed. What I want to do now is basically be guided by practical applications in safe AI. The reason is that there are so many degrees of freedom here on the assumption that you're using, that you are making on the kind of techniques or combination of techniques that you want to adopt, that it's a huge space. So I'd rather be guided by some concrete and useful applications for my research. So what does, for instance, learning models that satisfy the constraints in expectation, by construction means in this context? Well, structural learning can be learning the constraints if those are not or are partially given, of course. This is a very interesting problem that a colleague of mine, Samuel Kolb, and also Stefano Teso and Andrea Passerini have been working on quite extensively. Then, of course, also learning how this density function decomposes when to, for instance, split the space and fit two different densities, when to instead use a mixture model, or when to decompose the density. It's also interesting and very hard problem, actually. And then, of course, also fitting the parameters of this distribution. Learning constraints in expectation. So what we would like to do is basically having a hybrid semantic loss. So the weighted model integration equivalent of the semantic loss that I showed you earlier. Then, of course, the problem is computing this weighted model integral effectively, right? So we should now figure out whether we should target specific subclasses of a problem, whether to use knowledge compilation or just give up on an exact solution and rely to sample techniques. This also depends on the kind of constraints, of course, that we're interested in enforcing. Typically, people have focused on linear algebraic constraints plus logical constraints, but of course, the nonlinear ones are much more interesting. Think about physical laws, for instance. Most of them are definitely nonlinear. And then, of course, also what kind of models should we target, right? People have been working with piecewise polynomials because they're convenient to work with. They are closed under product, well, multiplication, summation, and also under integration. So if you integrate like a polynomial, of course, you get a polynomial. So they're nice from this perspective, but of course, they're not really good at modeling natural distributions, right? Most for instance, most neural networks actually parameterize distributions from the exponential family instead. Then we would like also to work on the third direction, verifying quantitative properties, not only on binarized neural networks, but in general other models. With SMT and probabilistic SMT, we can code a wide range of models, decision trees like SVMs, and also more fancy and popular models like ReLU networks and sum product networks, for instance. Here on the left, you see an example of a neuron with the ReLU activation function that is modeled using linear algebra. And then we would like to verify properties like group fairness, right? And we can do this with arbitrary priors over our inputs. The question is, of course, can we scale? And the only option, in my opinion, is focusing on very specific models and also on very specific properties. Otherwise, the general problem is so hard that there's no hope in scaling up to industrial-sized models. And now I have to congratulate with you because you made it to the last slide without quitting. So I hope I convinced you that weighted model integration is indeed a very general framework for constrained inference. I have not made any assumption in the definition of the problem regarding the kind of constraints that I want to enforce, or regarding the density functions, the kind of parametric families that weighted model integration supports. And I hope also I didn't scare you away from this very interesting topic of research. There are many potential applications of weighted model integration in safe AI. I haven't talked about the more theoretical challenges. I could go on for days, but this was not the topic of the presentation. Of course, if you have questions or you want to discuss about something, just ask me questions. And thank you for your attention.
Thank you, Paolo. Indeed, yes, you didn't scare us, and so I think there is time for some questions. So we have already the chat full, and I think that we can give priority to Sagar, that has a bunch of questions for you.
Hi, Sagar.
And then we have also Stefano. Since we are all online, I think that if possible, you can unmute and ask yourself a question to the speaker. So Sagar, if you want.
Sure. Okay, so the first one is, I think, a detail. So semantic loss, I saw the parameterization. You show it to be parameterized by theta and 1 minus theta. And I imagine, so if
yes. Let me go back to the slide.
So, I mean, as far as my understanding of weighted distribution goes, I think this is strictly less expressive than weighted model counting. So if you have arbitrary weights,
okay,
you will be more expressive, definitely. So I did not know anything about semantic loss. Just so my question was, is this a real restriction, or you just wrote it for explanation purposes?
So what I reported here is, as far as I remember, the definition.
Okay, by definition.
The definition that was given in the paper, but notice here that these thetas are the output of your neural network, right?
Okay. Well, no, I did not understand that. I thought they are user-defined constraints.
Yeah, I kind of skimmed through that. So I'm assuming that you can have like any differentiable function, but this function basically parameterized, as you see here, like a distribution over logical propositions, right?
Okay.
So you don't get the weight of a negation of a variable. The weight of a negation by let's say by definition is 1 minus the output of your neural network.
So
that said, if you had a model that gives you also unnormalized, let's say, weight that is not between 0 and 1, right? You could still use the semantic laws.
Okay, okay, it's clear to me now. Yeah, thanks.
Yeah.
I also understood it wrong in the first pass, I think.
No, definitely. So basically, what you would get instead is like a normalized probability mass, which is then the mass that the model puts inside the constraint region, let's say. But it doesn't really matter even if you don't compute like the normalizing factor. That's just gonna be like a scalar value renormalizing your semantic loss. So ultimately, it doesn't really matter.
All right. So I'll just brief. I will make my second question smaller. Just a reference to the paper that you mentioned about the neural network to the
yes.
To the SAT conversion. You said that every neural network can be converted to a MILP problem, mixed integer linear programming. Yes.
No. Wait. No. What I said is that binarized neural network can be converted to.
Okay.
So yeah, these binarized neural networks have certain properties, like the weights are either -1 or 1, and the output is really a binary output. So you have a step function here.
So this is some 2019 paper called.
No, so these binarized neural networks actually predate that paper and are used, as I mentioned, are used in mostly in embedded systems. There's I don't remember the year, but there was like a paper, I think it was 2018. I can send you the references if you're interested.
It would be nice. Yes.
That basically was concerned with qualitative verification of these networks. So really just doing verification by means of reducing the problem to a SAT problem, right? This is what most works on neural network verification are concerned with. The paper I'm referring to instead uses weighted model counting. And this is really the novelty of the paper that I mentioned. So instead of verifying properties like yes, no, like is this network safe to adversarial attacks? Yes. Not this. They basically try to compute probabilities or to quantify how unfair or conversely how fair the network is using weighted model count. Really model counting. Yes.
Is this by Kuldeep S. Meal, where they use approximate counting? Okay. Yes, I see. Yeah.
Yes.
Last question, really last. So you said there are some tractable subclasses of weighted model integration as well.
True.
So what are these?
I'm gonna point you to the paper that I wrote with people at UCLA 2 years ago, because the characterizing the tractable class is not easy. It's gonna take like a while. I can briefly kind of summarize it into 2 things. Well, first thing is that integration should be tractable. So your problem need to have some density function that you can tractably integrate. Very generic, but like for instance, polynomials have this property, or log polynomials have this property too. Log linear function really, because otherwise you are not closed under integration. And then you need, of course, the tree width of your problem must be 1, but this is not really surprising. This is true also for purely discrete models. The novelty in the hybrid setting is that the primal graph, so the dependency graph of your problem, where like nodes are like the random variables and edges are like the dependencies, should have logarithmically bounded diameter. And this is not true in the purely discrete case. So say, for instance, that you have like a path graph and you want to do belief propagation on it. That's okay, right? The tree width is 1, and you can just send messages along the edges of this primal graph, right? But in the hybrid case, your messages are really piecewise polynomials. And each time you basically marginalize one variable out, the size of these messages grow exponentially. So you also need a logarithmically bounded diameter in your graph.
All right.
I'm gonna send you the paper in
Sure.
any case. So maybe this is too hard to explain in a few sentences.
But also I lack the background, I think.
Okay.
But thanks a lot.
Thank you.
That was it. Yeah, thank you.
I cannot read the chat from here unless I am sharing the slides.
Yes, there is this question from Stefano.
Yep.
I don't know, Stefano, can you hear?
Can you hear me?
Yes.
Yes.
Okay, great. So, all right. So I guess my first question is, there is a trend of building neural models to solve combinatorial problems. Like, you have these neural networks or graph neural networks, whatever, that are used to solve SAT or that try to approximate the problem. So my question is, have you thought about, or is it conceivable to do something similar for WMC or WMI?
For WMC, yes. Actually, there's a work by people in Oxford that used graph neural networks for solving weighted model counting approximately if the weighted model, if the problem is specified in no wait.
DNF.
Yes.
In a DNF.
In DNF. Yes. Right. In DNF.
Thanks.
And yeah, I was kind of mixing two works by the same group because there's another paper by the same group that actually have proposed an approximate algorithm for weighted model integration. Again, when the problem is in the DNF.
So that's not neural.
That's not neural. No.
Okay.
No,
all right.
no.
Okay.
Of course, people have tried using this for counting problems. There's also some work by Stefano Hermon's group in Stanford that basically generalized belief propagation by using some neural predicates some neural networks as aggregators of messages. So instead of using like traditional loopy belief propagation, you use instead of using like the standard way of aggregating messages, use neural networks for that. And they actually applied that problem to weighted model counting too. And if I remember correctly, because then there's another work on the same year by Max Welling. So one is called belief propagation neural network. The other is called neurally enhanced belief propagation, and they're doing very similar things. But yeah, definitely people have tried solving counting problems, although most people really focused on approximating decision and optimization problems with neural nets.
Okay. Thank you.
Thank you.
So I have a couple of other questions, if you don't mind.
No.
Okay. So I guess the second one is, how long will it take until we can verify decision trees or even neural networks learn from data? Meaning in terms of, those properties that you mentioned, so really probabilistically and including continuous variables. So are we there yet? Or what's missing to get there?
So this morning I was writing some benchmarks. I was trying to generate some product networks and try to run our latest solver on those problems. But that's just for saying that I'm actively working on that. Let's say.
Okay.
I don't have an answer, of course, when it comes to real world or like industrial sized models. That I don't really know. We haven't been trying solving or verifying large models yet. This is really something we are starting to work right now. There's a paper that's currently under review where we well, that I shouldn't say, right? Okay. I'm not gonna say.
There is no such paper.
Okay. There is no such paper. I'm gonna tell you offline.
All right, so thank you. Let me go straight to the third question, which is it possible to learn models that are naturally easy to verify? For instance, by regularizing the learning procedure appropriately somehow.
Yes. So I recently stumbled upon a work where basically they were trying to learn a neural network that was provably easy to verify, and I think that that's actually like a great idea. So my hope is that if I don't manage to, if we don't manage to write some procedures for verifying general, say, ReLU networks, right? Because we don't manage to scale quantitative verification to large models, then at least we can understand why. So what's the problem? What are the kind of assumptions that would make the problem easier? And then what we can do next is that we can learn some models where those assumptions hold, right? And that would mean that we basically sacrifice some performance for the guarantee of having a model that can be verified. And then I think that that's great. I mean, in some applications, you'd rather lose some empirical accuracy or performance over, you know, some guarantees.
That makes a lot of sense. So thanks so much.
Thank you.
I'm all out of questions, so thank you.
Cool. Okay, thank you.
Cool. Thank you, Paolo. So I think we have time for one more question, if there are some. Otherwise, we can conclude here. So thank you very much, Paolo.
Thank you, everybody.
It was a great pleasure to have you again, but unfortunately on Zoom. So
Next time.
Till next time.
Yes.
Thank you.
Enjoy the rest of the event. Ciao.
Thank you.
Thank you.
Thank you. Goodbye.
Bye-bye.
Bye, everybody.
Thank you. Bye.